In-class activity 14b, inverses of functions with fractional exponents. 1. In addition to degrees Fahrenheit and degrees Celsius, scientists sometimes measure temperature in degrees Kelvin and degrees Rankine. The two temperature scales are related by the following equation. K equals Rankine degrees minus 491.67 over 1.8 plus 273.15. If you knew that an experiment should occur at 298 degrees Kelvin, explain how you might determine the temperature in degrees Rankine. Well, to solve for degrees Rankine in the equation, you'd first have to subtract 273.15 from 298, and then multiply by 1.8 and add 491.67. Objectives for the activity. You will understand that if f inverse is a function that reverses the process of function f, then the two functions are inverses of one another. If some functions do not have inverses without some functions, do not have inverses without restricting the domain of the function, you will be able to find an inverse for a function with fractional exponents and evaluate and interpret equations written with fractional exponents. 2. In lesson 10, you learned how to find the inverse of a quadratic function. In this activity, you will follow a similar process to find the inverse of a function with a fractional exponent, and you will compare properties of the original function with properties of its inverse. Part A, consider the function f of x equals x to the 1/3, where f of x equals y. Evaluate f of 27. So if we were going to evaluate f of 27, simply we know that this is the x would be replaced by 27. So we have f of 27, and then equals the x again here is the 27, and we're going to raise this to the 1/3 power. And we know the 1/3 power is like taking a square root, or a cube root, so the cube root of 27 is going to be 3. Let's move the screen up. That was part A. Let's do part B. Part B, it says, use your graphing technology to graph the function f of x, and what are the domain and range for this function? So if we go over to our calculator, and I'll go to the y equals screen, and we want to graph x to the 1/3. So we can write x, whoops, what happened here? Let's clear that and start again. 1 second. Okay, we're back. Use your graphing technology to graph the function f of x. This is part B. What are the domain and range for this function? So on the y equals screen, I'm going to write x and raise that to the 1/3 power, and then we'll graph this. So I go graph it, and there we go. And just by looking at this is just a small part of this curve, but you can see that it's going to go to the left forever, to the right forever, and it's going to go up and down forever. So that we could say that the domain of the function is all real numbers, as well as the range is also all real numbers. So let's go back to our writing here, and we could say the domain of this function f is all real numbers, and we could say the range of f is all real numbers. There we go. Part C. What would undo the cube root of x? Find the formula for this inverse function, f inverse of y, and explain your answer. So what would undo the cube root? Well, it was, let's see, we did have, why don't we write it like this? We'll write y is equal to x to the 1/3. And we can solve for x. We do that. We would solve for x. We could write, take the cube of each side, and then we would end up with x is equal to y cubed. So we could write this, instead of x equals y cubed, we would write f inverse of, well, the normal notation is x, but for right now, we'll just keep it at y for this section, this step here. F inverse of y is equal to y cubed. So for part D, in part A, you found that f of 27 equals 3. Evaluate the formula you found for the inverse function in part C using y is equal to 3. To help check that you have the correct formula for the inverse function, did your inverse function undo the original function? So if we write this out, we could write f inverse of 3 is equal to, well, the inverse function cubed the input, so we'd have 3 cubed, and that would lead to 27. So yes, the answer agrees with our earlier calculation. Part E, to graph your inverse function, don't forget that x is now graphed on the vertical axis and y on the horizontal axis. To allow you to graph the function, you will need to switch your x and y variables. This equation where the x and y values are swapped is the standard way to write an inverse function. What will the inverse equation you are graphing look like using the standard notation? And this is what I started writing earlier. So the standard way of writing that would be f inverse, and instead of writing y like I did earlier, that was supposed to be an x, so we'd write f inverse of x equals x cubed. Part F. In the same window you used to graph the function in part B, graph the inverse function, f inverse of x. Does f inverse of x still meet the criteria for a function? And what is the domain and what is the range of this inverse function? So back to our calculator, and we'll go to the y equals screen, and let's go down to the y sub 2 line, and we are going to write x cubed. So x cubed, and we're going to graph this, and there we see we have two curves graphed on the same line, or the same coordinate axes there. And we can see that f inverse is still a function, and we don't have to restrict the domain or anything, but the domain and the range of the inverse function is, again, all real numbers. Part 3. For more complicated functions, we can use a method of decomposing function and then undoing it to help us find the inverse. You saw this method earlier when working with quadratic functions. In this question, you will revisit Kleiber's law, which describes the relationship between the mass of an organism and the organism's metabolism. Part A, decompose the function R is equal to 70m to the 3/4 power, where m represents the mass of an organism measured in kilograms, and R represents the metabolic rate of the organism measured in food calories or kilocalories per day. By completing the diagram, begin with your input variable m. So let's scroll up here. Let's not, there we go. I'll leave the part A there at the top. So the input to this, we would say, is just m. And then we want to raise m to the 3/4 power. So I'm going to put here, raise m to the 3/4 power. And we'd end up with m to the 3/4. And then the next thing we want to do is we want to multiply by 70. So we'd have 70 times m to the 3/4 power. Part B, this time with the output and this time begin with the output and reverse the process so that your final box is m. In other words, undo what was done to m in the original function. So to undo this, we'd begin with where we left off. So it would be 70 m to the 3/4 power. And then to undo that, we would start by dividing. Divide by 70, and we're left with m to the 3/4 power. And then we want to raise what we have here, the m to the 3/4 power, we want to raise that to the 4/3 power. So we are going to raise m to this 3/4 to the 4/3 power. Trying to squeeze everything in here. There we go. So we'd have m to the 3/4, that all raised to the 4/3. This will simplify to just m. So that's part B. Moving on to part C, using graphing technology, graph the function that we've been working with using the window, okay, -100 to 10,000. That's going to be on the x-axis. The y's are going to go from -100 to 100,000. And let's start by doing that. Let's go back to our calculator, go back to our y equals screen. I'm going to even turn those two off and move to the y sub 3 line here. So let's graph 70. And then we don't have an m, we're going to use x. So x raised to the 3/4 power. And then they want a window that's -100. So let's see. I'm going to go to the graph. Whoops. 1 second. Okay, we're in the window screen here. And we want to make the x min -100, the x max 10,000, and then y min is going to be -100. And then finally, y max. This is 100,000. There we go. And let's just graph this. There we go. I'm even going to move this all around. There we go. And we can see clearly what this looks like, at least over this domain and range. And the question is, will the inverse relation for Kleiber's law also be a function? Well, at least for this part of the curve that we see, it looks like, yes, it's going to be a function. And its reasoning would be it's a one-to-one function. So let's move on to part D. Write the inverse function for Kleiber's law by solving for m. Okay, I'm just going to move this up a little bit. So we want to write the inverse function for Kleiber's law by solving for m. And here we go. I'm just going to write r is equal to 70 m to the 3/4. So to undo this, the first thing I think I'm thinking to do is divide by 70. So we get r over 70, and we're left with m to the 3/4. And then from here, why don't we raise both sides to the 4/3 power? So I would, if you want to see the step, we went 4/3 here and 4/3 here. So that would leave us with m is equal to r over 70 to the 4/3 power. Okay, part number 4. In class activity 14A, in that activity, you found that the function for the heart rate of small mammals to be h is equal to 241 times m over 1,000 raised to the -1/4 power. H represented the approximate number of heartbeats per minute, and m represented the mass of the animal measured in grams. So part A for number 4 says use the process in question 2 to write the function by solving for m. So let me just start by copying this down. All right, why don't we divide by 241? So we'll start the same way that we did in the previous part D example. And from here, why don't we raise both sides to the -4 power? And that would leave us with, I'm going to write this on this side here. And then let's multiply by 1,000. So we'd have M is equal to 1,000. And then we have 241 over H to the negative 4. Oh, look what I did. I switched this. I did 2 steps in my head here. Let's cross that out. I'm going to go this way here. We're going to end up with M equals 1,000. And then we have H over 241 to the negative 4. And to get rid of the negative exponent, we could always write this as 1,000 and then put the 241 in the numerator, H in the denominator, and then we have positive 4 instead of negative 4. Sorry about that. So part B, recall from in-class activity 14C that a mouse had a heart rate of 658 beats per minute. Use your inverse function to determine the mass of the mouse. Does this agree with what you found in the previous lesson? Okay, so let me get rid of this stuff here so it's not in the way. And back to writing. So we have M is equal to 1,000, and we'll have 241 over 658, and that's going to be raised to the 4th power. So let's go back to our calculator and see what we come up with. Get rid of that. Home screen, we have 1,000. And then we'll do 241 divided by 658. And this is raised to the 4. We get about 17.99, okay, about 18. And that is what we got last time. So this is, we'll just put equals 18. And that is in grams. So that's what we got last time. So yes, it agrees. All right, that's the end of this lesson. Thanks. Bye.